Hi, everyone. Is everyone actually awake? Cool. I don't know if you guys saw, but the volcano is exploding, which I heard it felt like a really good omen for my talk. I don't know why, but I felt like an exploding volcano could be good. So anyway, thanks for the introduction, and I also wanted to thank everyone for setting up and working this conference, because I feel like all the logistics have been absolutely incredible, and so we should all be very thankful to everyone who put a lot of time in. All right, so as the introduction said, I'm going to talk a little bit about how I think we can get science to work a little bit better pretty quickly in a lot of different ways. And so the title of my talk ostensibly is Improving Science Through Better Software Engineering. That's where we go. That's where we're going to start from. So I like having a lot of cool, fun pictures in my talks because I find like they're better than words. But because there's so much machine learning these days, I figured I would just get an ML model to write all my pictures these days. So we can do a little bit of guessing where I'm going to put up a picture and you guys can guess what the prompt was to get it to make this. So if anyone wants to guess, please scream out as loud as you can. And if no one screams out, I'm just going to stay on the slide for 30 minutes. Anyone have any ideas? Sorry? That's pretty good. It was just pencil drawing of a TED Talk, and it just drew this. That's great. Now, so why do I have a picture of a TED Talk? Well, I assume a lot of you guys have seen TED Talks in the past, right? And so it seems like the one thing they always tell you in TED Talk training or whatever all these people go to is you got to ask questions to the audience, otherwise they fall asleep or maybe they don't care or whatever. So who am I to argue with TED? So I'm going to start with some questions. So you guys are probably all researchers, and you're probably all really smart researchers. So I have some questions for you. Who here has written software as part of some of their research? You put your hands up. All right. I don't know what the rest of you guys are doing, but I'm kidding. Who's tried to reuse scientific code in your research? Great. A lot of people have tried to do that. That's good. It's good. That's a scientific process right there. All right. For those of you who are clinical, I don't know if there are any doctors here, has anyone here made a decision based on some research that was computational in nature? All right, a couple people. Awesome. Now, has anyone failed after trying hard to reuse some code, either your code or someone else's code, because you couldn't get the dependencies to work properly? All right, look, there's some people failing here. And who here has written a lot of code without tests or design? I'm putting my hand up too. Great. And I think this is the big one. Who is worried that they have some bugs in their code somewhere that might be affecting their answers? This is true for me too. All right. Well, this is sort of what the inspiration for why I'd like to talk about this. So I'll give you like a quick 30-second spiel about myself. Like, who am I? I may be a little different from a lot of the other speakers here. So that's what I usually look like. Not actually true, but that's kind of what my mom wishes I would usually look like with a suit. And you can take a picture of the QR code. It's just my website. I went to Carnegie Mellon a long time ago in grad school, and I studied distributed systems. So I was basically doing computer science and electrical engineering stuff. Then, over 20 years ago now, I went to go work at Google, and I built a bunch of the distributed systems there. And worked in mobile and ads and stuff for a while. Then I left and had the fortune of investing in a lot of companies, and it let me see a lot about how new engineers like get together and learn the skills they need to do to build what's important. I started a company. I ended up selling that to Twitter. I ran the New York engineering office there for a while. So I managed like large engineering teams with a lot of junior people. I spent some time in the investing world at Benchmark, which is an investment firm. Then a friend of mine convinced me to go help out one of his companies, a cancer immunotherapy company. And this opened my eyes up to a lot of what we could do across the industry boundaries. Because I saw a lot of really smart people who were doing some really interesting stuff, kind of getting slowed down a lot by problems that I had seen multiple times in my career. And they're not exactly the same problems, but they're close enough that I was like, oh, I know how I can make everyone here substantially more productive with a little bit of work. So, I trained a couple of the scientists, and it seemed that it worked out better for them. It's not clear if this company is going to do well or not. I don't know, but they were individually more productive. Then I gave a bunch of talks about this, essentially like how do you use software engineering techniques to improve the quality of your scientific work and your speed. And now I teach this in a class at Stanford to grad students once a year. So that's my quick background summary. And let me get on a little bit of a soapbox here. I think software engineering and science can be poor. And I think it delays our future by 5 to 10 years, is my sort of guess. And the reason, of course, is because it makes our conclusions less confident, and it prevents us from attacking bigger problems with larger groups of people effectively. And I've seen this happen in the tech world as well, and I can see it now here too. And I think one reason is because 20 years ago in science, most of the software was done post hoc. So you would go out, do your analysis, and then you have a bunch of data. And then you say, okay, I'm going to analyze my data. And then I write a little bit of code to analyze a small amount of data that I can look at and sort of verify by looking at it, squint, that it's kind of mostly right. But today, this isn't the case. Today, it's pervasive. It's everywhere in your research, in a lot of fields, and in genomics, and even in ecology. There's a student that took that reached out to me. Is like even in ecology, there's like people will use a lot of scientific software. But on the bright side, I think there are large improvements. We don't have to be perfect. Just getting sort of good can make a huge difference. So. Finally, I think you guys can help, and maybe you'll get some ideas, or maybe you can come harass me after when I'll be sitting at the beach. But I'm happy to talk about this. But before I go forward, here's another picture, which you guys can take a second, try to guess what this was. It is a one-line drawing of the Brooklyn Bridge, which is actually pretty good for a machine learning model. So why do I have a picture of Brooklyn Bridge? Well, because I want to talk to you a little bit about the difference between computer science and software engineering. And a lot of people here have taken computer science classes, for sure. And computer science it teaches you the theory. It teaches you, there's a machine learning model. How do I make it have twice as many parameters? What are the algorithms I use to do a better gradient descent? But software engineering is different. It's applied. It's kind of like if I went to your universities and got the best physicist, and I said, hey, I need to get the other side of this ravine. They could probably build me a bridge that was pretty good. But then, if I wanted to add a bike lane or put some lights or do some maintenance, and I hired an engineering firm, they would come and look at this bridge and be like, I have no idea how this bridge even stands up, and it is probably simpler for me to tear this bridge down and build you a new bridge using standard components than to try to go and modify the bridge that this physicist built. And this is basically what software engineering is all about. It is the equivalent of civil engineering to physics. It is how do you make a systematized, lifestyle-centric, disciplined approach towards creating software where you use as many reusable standard components in as much of a repeatable way as you can so that if someone else comes and looks at it, they already kind of understand a little bit about how things are going. So this is the difference. And here's another one of these pictures. If someone wants to guess what this is, feel free. But this was just, I had to add multicultural because otherwise it was all just white people. Very strange. But basically, this is like a high school debate team, and this takes me back when I was in high school on the debate team. They would always tell me, if you're going to make a point you want people to remember, you got to say what you're going to say, you got to say it, and then you got to say what you've said. So this is my attempt to hold true to Mr. Allison. I think I want to show you that scientists believe scientific code is not great, not just me. There is hard data to confirm it, that there are mistakes that we can find from poor software practices, that they are exacerbated by and also do exacerbate reproducibility woes, which is a big problem facing science today, that educating people can help, and that funding agencies really have a part to play. And finally, you can't just use software engineering technique examples and guidelines for the folks I used to work with. Like, if you're building if you're building Google Compute, you have different standards for what software engineering and testing needs to be than if you're doing an experiment. So if you just Google, how do I test my code and try to do it, it's way overkill. And I think it can push people away from what needs to be done. So here's an example of something that is linked to from a paper that I found. I'm sorry for those of you in the back if you can't see it. I try to make it as big as possible. But here's an example. So this is like code that was submitted and linked to from a paper. So what do you guys think about this? Right. They need to improve their naming scheme. Good point. Why are there 27D, there is run rail fun, whatever, 17B. So this tells me that people are just like making random copies of stuff, right? Okay, do you trust whatever version of this resulted in the paper? I mean, maybe, I don't know. It just doesn't smell too good, but maybe it's all right. How about this? This is a snapshot of another paper. This was I think over 5,000 lines of this, over and over again with slight variations. And so what do you think? Like, do we have confidence, just looking at this as smart people, would you say you have confidence in the output of this software? Maybe, right? Maybe. It could be great. It could be terrible. We don't know. I look at it, it seems a little scary because I have no idea what's going on. Here's another example. What do you think about this? Do you think you could, if you looked at this, do you think you would have more or less confidence in this code than the rest of the code? Okay, so some people think this has less confidence. It could be. Who knows? This is some examples. I would say, having reviewed a lot of code, I would say this probably, I would have more confidence in this because I look at it, there are blocks of code. Variables maybe don't have great names, but there are comments that explain what this thing does, and maybe I don't know what they're actually doing, but if I look at it, I have some confidence that I can understand what is actually going on here, right? Okay, so what do? The first thing I said I was going to show you is that scientists themselves believe quality code is poor. So I talked to scientific friends. I worked with Mike Stadler, who was a postdoc at Berkeley. We talked to a bunch of people, and this is basically what they said. Nothing surprising. Scientific code is hard to use. It's easier to rewrite from scratch. Sometimes it's so hard to figure out whether it works and what it's doing. I can't even run my own software, stuff like this, right? Nothing too surprising. And so I would say that at this point I've shown you the first thing, that scientists themselves believe that scientific code is not great. Maybe you guys don't also believe it's not great. But of course, this isn't science. Like me just going talking to 20 people and asking you guys what do you think is not actually science. Is it true? Is it biased? Is it just that we're looking at like the 5 worst papers and this is what we find? These two guys holding a gigantic slide rule would agree. So I guess it's research time, right? Like it's time to do some research, and maybe we're Doc Brown and we got to do something. So the first question we asked ourselves is, okay, how are we going to actually show this? It turns out that one of the best things that happened to science recently, or hopefully none of you guys work for any large European companies, but one of the best things was these open source journals, which I think is amazing because you can just download a bunch of papers. So we downloaded 1.5 million papers from a corpus, and we just analyzed them. We were like, let's look at references to software first to see what languages are people using, and are people using more languages than they used to before, more algorithmic kind of work. And it turns out that they are. These data are not completely unsurprising. So if you go in the last 20 years, across most disciplines that we looked at in this potentially slightly biased source, but 1.5 million papers, we see that there is a large increase in the number of papers that reference some kind of code, right? And I don't think that's surprising to anybody here. Another interesting thing is if you normalize it, you can see that you can look at old languages. Old languages are things like Perl and Stata, and you can see, like back in 2000, there was a lot of people writing in Perl in these old languages. And new languages are things like Python and R, basically, is almost all of the new languages. And you can see that R and Python are growing massively, and this is even from 2 years ago. But R and Python are kind of taking over the world here. Okay, well. How are we going to? I talked a little bit about. These data were just from looking at the sort of text of the papers. But what I was trying to show you again was that the code isn't good. So how are we going to do that? It turns out that a lot of journals are requiring people to link to code. And oops, I don't know what I did, but I did something terrible, and it has gone off. What did I do? I don't know what I did. Anyways, it turns out that a lot of journals require people to link to code, and there are 70,000 GitHub repositories we were able to find. So we just downloaded them all, and then we started analyzing them. We wrote some static analysis code that counts the length of blocks, which is like how many lines of code without a parentheses or without something else like if statements, that kind of stuff, functions. We looked at how often are people copying and pasting code with slight modifications. It's actually kind of complicated to do this right, but we did it. We looked at comments, we looked at variable names, we looked at tests, we looked at dependency management, and finally, we tried to figure out if the code would run, but it's basically impossible to get it to run automatically. It's even doing it manually. I tried 5 repos, and I couldn't get any of them to run manually. Either the code didn't work, there were no dependencies, or I couldn't find the data, so I have no idea how to do that last part. So looking at the median and interquartile range, we have a control group, which is, we looked at bioconductor, which is an R library, basically packages of R libraries, which we expected to have higher quality. And here's a couple of examples. Block count per line of code. It's basically the higher, the better. It tells you the number of blocks that you have essentially in your code. And generally, the higher, the better. And with tests, you could see that the control group has a lot. And these other things are S's like singletons. So these are repositories that are referenced only by one paper. And L, M, and H are sort of low, medium, and high references. So essentially, as code is used more often, we see slight trends, but we don't know if we can count on that for block count. But functions with tests, it's pretty significant. And if you just take a linear combination of all the things I mentioned before, you get a score that looks kind of like this, where the curated sort of control group is, I don't know if it's control, but its curated group has a high quality, and the rest have low. This sort of aligns with our intuition and my sort of experience of 20 years of looking at code. The stuff that is written by people that take a lot of care or that have experience in software engineering, which is most of the people writing bioconductors, turn out to be better and they're used more often. All right, so here's some information maybe that I've shown you that there's some data, but, and it's a combination of sort of intuition of people who've been in the space plus a bunch of data. I don't have time to go to all the slides because I only have 30 minutes to talk and I want to get through the stuff. So, okay, so now there's a forest over here with a lot of smoke in the style of Starry Night, but so I feel like I may have told you now a little bit about some smoke. But the question is there any fire? So yeah, I'm telling you code quality is not good, but is this actually truly causing any problems, right? Because maybe the code quality is just not good, and I'm this crazy engineer who wants everything to be perfect, and in reality, science is not like this, and we have to be able to tolerate some code written by people that are just writing code. But okay, so let's look at some retractions. Here's a retraction that was in Science, and it has an extremely long title, which I put at the bottom. But basically, this paper is cited by 300 plus people. And everybody here was very ethical. There's no malfeasance whatsoever. So let's get that clear. So these guys reused code from another lab. And they were building their paper. And they came with some cool conclusions. But there was an error in the code that flipped the structure of, I don't really know enough to know what this is, but it's some structure of something that got flipped. And this basically invalidated their conclusions. But they didn't have any automated tests, and they didn't really use any sample data to verify this anywhere. And then 300 people who cited them, this resulted in multiple other papers' retractions. So if you want to read more about it, you can take a picture of this QR code and read all about it. So here's an example of poor software engineering leading to a retraction from Science. Okay, well, that's not good. So here's one example. Here's another example in JAMA. So these guys wrote some code. They were doing some randomization, and they were trying to there was a randomization of 1 or 2, and to do some other thing in their code, they needed it 0 or 1. And so they wrote some code to do this, and it turns out that the mapping code was not tested, and they resulted in inverting the arms. And so what they wrote in their retraction notice was that the correct results reversed the main finding. So not only was this ancillary, it literally came out with the opposite finding of what they wanted. This thing was cited by almost 100 people and was published in JAMA, right? So, I don't know enough or really anything at all about the paper situation, but if you take a picture of the QR code, actually I think the title may not be right, but if you take a picture of the QR code, you can read more about this. And here's another one. This one, I was explained to you by statisticians, may or may not actually be a programming error. it might just more be a conceptual error of people not understanding what's going on. But if you look in R, there's a function called correlation, which I'm sure many of you used. And if you use it with this argument pairwise, it essentially ignores, I mean, you can look at this later, but it ignores missing data. And apparently, I'm not a statistician, but apparently, if the data that are missing completely at random, this is probably something that's reasonable. But these guys, I guess their data set was not like this. And they assumed that the option would exclude incomplete records. But it turns out that it doesn't do that, and it did something completely different. And again, their conclusions were at risk. Now, is this a programming error? Well, not really. It's basically an error that they used this function and didn't understand completely what this argument does. It may not be obvious to someone who's not a statistician, but the code was not tested. So they didn't write a test with data that looked like the data they collected and do a mental check or some kind of check to see, does this make sense? So when we saw this, a little light bulb went off in our head, and we said, is this a one-off? We just downloaded 30,000 repositories in R, 70,000 total repositories. It would be pretty trivial to just look to see if anyone else is using this function. Well, it turns out that 5% of people, right, who have R repository, who have any R code at all, use this correlation function with this argument. And fewer than half, or less than half of those, have any tests at all. Now, what does this say about the reliability of this research? I have no idea, because maybe all these people really understand how this function works, and they're doing it in a reasonable way. Or maybe they're not missing any data, and if you're not missing any data, this function does exactly what you think it does. Or maybe they're missing data, and they didn't test it, and their conclusions are wrong. I have no idea. And I looked at a couple of these repos, and I don't understand enough of the domain knowledge or statistics to know whether or not there's a problem. But I don't know, if we have 5% of 30,000 repos, 2% of 30,000 repos, which do not have any tests that use this function that has already resulted in a retraction, I don't know, probably something in there is not right, but I don't know for sure. So, all right, I can tell you that I think I've shown you that mistakes have arisen from poor software practices. There are many more. These are 3 examples I cherry-picked. So let's talk a little bit about reproducibility. So there are a lot of people here who are working on a lot of really interesting things, and I learned a lot from the last couple of days sitting in these talks. So I'm going to walk through an example I made up here that maybe can be a little reasonable. So imagine we have an MRI machine, and we're MRIing a bunch of people, right? Like a lot of people. And we have 20 years of data with what the patient symptoms were, let's say, the MRI data, and then what their diagnosis or outcome became. All right, this seems already sort of reasonable, I'd hope. But then now we're real good modern researchers. So we're going to feed this to a neural network, right? And then we're going to make the neural network make us a lot of money. I'm sorry. I've been spending too much time with entrepreneurs. We're going to make the neural network actually make a lot of people healthy because we'll be able to predict when we have to do some intervention. All right, this seems good, right? This is great. We're going to take some MRIs, we're going to predict that we're going to save some lives. This is what we're here for. All right, so this is a simple illustration. Let's say we go to MSK, we get a patient ID, we get some MRI data, and we get some diagnosis. So diagnosis is what comes later, which is why it's black. We're going to build our ML model version 1. We're going to use all the coolest ML stuff that you guys have learned about and we'll learn about in this talk, in these talks today and this week. And we're going to make a predicted diagnosis based on what we have. It's pretty easy. Like our MRI image data maybe is in our huge data file. And then we're going to do an analysis, right? So we do this and we find that things don't work so great. We keep iterating, and eventually we realize we want to have our colleague look at it. So we copy the MRI data to some USB sticks so they can look at it. We have an MRI file name now in our input file, and we do some analysis. It's working okay, but unfortunately my PI is kind of a hard ass and says we can't publish it yet. Got to go back, work harder on stuff, and eventually we get analysis version 19, ML model version 8. We moved our MRI data to S3 because the journals made us do it, and now we've published our paper, and we got into JAMA, and this is awesome, right? Like, this is great. I just need one more paper, and I can get my PhD and get out of here, right? So we keep working, and we decide the feedback we get is we need to get multiple hospital data, because maybe this is specific to this one hospital site. So now we have a new data set with an augmented data set with a hospital name in there too. The rest is kind of mostly the same. But we added some Canadian data, and so now we have to use ICD-10 instead of ICD-9 codes, because there's Canadian data and they use different codes. All right, So we got this thing, we're ML model 22, we're analysis version 14, we get the second paper, we're pretty much ready to go, and I'm very excited because we followed the best practices. We stored our ML model in GitHub. We have our CSV files on the university servers or on S3. We put our MRI data sets there. We submitted to preprint so everyone can read it, also to Nature, which maybe people might not be able to read it unless they pay a lot of money, but you know, what could go wrong? Does anyone have any ideas of what could go wrong here? Shout it out, guys. All right, someone in the back. Right, did you test it? Well, that's one good possibility, yeah, did you test it? Well, it turns out that's a great point. Maybe we didn't test our code. And maybe we didn't have our friends look at it. That's one thing that could go wrong. Anyone else have any other ideas? Yeah, in the front. Data drift. All right. Now this is sounding kind of interesting, right? So one thing I want to show you or talk to you a little bit about is animations can be bad. All right. So we were here, and what if someone comes back to us and says, okay, hey, you know, for paper one of the papers you cited got retracted. We don't think it affects your results. Please rerun your analysis of paper one. So who knows, who can remember what version of the code we used to generate paper one, who can find it, and who knows what version of data we had to use to run with version one. Even if you have all the code and all the data, how do you know? What if you try to use this data file with the old code, or the old data with the new code? Like, how are we going to keep track of this, right? Did we test it? And sorry with the animations, but the other problems could be our institutional servers might be non-archival. The CSV data could just disappear. Cloud services is something that came up in the workshop. Cloud services cost money. And when I graduate and go away, who is going to make sure that someone is paying the Amazon bill so that my files don't just disappear off S3 and no one can ever see them again? What if there's a mismatch amongst the code, the libraries, the data? You know, what if there's version mismatches? Which versions generated which paper? And of course, there's patient privacy. I just uploaded all of these files to S3. Was I even allowed to do that? Like, is it okay? Like, is there encumbrances? Like, what's going on here, right? So there's a lot to think about here, and there are some solutions. You know, we want to share our code on our data. We should version our data and the code. The code should be on source control. The corpora of different sizes have different encumbrances. So if we just have X-rays, maybe we can store it someplace, but if we have full MRIs, we need to store it somewhere else, and we got to be able to share the data, because if you don't share the data, it's not science, right? And I think, you know, there are lots of places you can go. How do you know which one to do? I suspect that there are, you know, there are good things we can learn here, but when it does work, if you look at COVID-19, a lot of things went very badly with COVID-19, but some things went very well. Like, the genome was shared pretty widely, and most of the work was published, and you could access everything, and people were sharing their data in some way that you could access it. And it, I think, let us really, at least in some realms, move pretty quickly. All right, so what can you do? Try to write a design doc, just like you wouldn't do an experiment without, you know, without having a experimental design. Do not write code unless you have a design. It doesn't have to be complicated. I'll share later some stuff about it, but you don't need it to be complicated. You want to have a plan for reproducibility. How is someone else supposed to find your data and reproduce it? Your institution can help. Stanford has a lot of people that can help with this kind of stuff, the librarians, a bunch of people. Try to use existing tools where you can. And cloud providers can help. Like GCP was here earlier. I mean, if you have a lab that is computational, if you email them, you'd be surprised how quickly some of these people will get back to you to try to help you. And following best practice in software is good. Like, I can't go into I only have 30 minutes. I can't go into it in detail, but there's stuff that we can do. And we can do it with education. But before we go to education, I want to reiterate, scientists are not lazy, not sloppy. You know, maybe they are, but that's not the main point. I'm not saying that we need to be world-class engineers here. And I'm not saying that computer scientists are amazing. I've trained a lot of junior CS people who don't know this stuff either, and we learn in industry by apprenticeship. And you kind of should too. So if you know how to do this, make sure everyone in your lab learns, right? So basically, I have a class that I teach at Stanford that is specialized for academics. We need to do hands-on training. you can't just tell somebody what to do and expect them to do it. This is a thing that you've just got to actually be forced to do once or twice. And we need a carrot. The incentive structure is not aligned to make reproducible research or good quality research, so somehow we've got to get it so that your career is positively impacted by doing good scientific work. And at Stanford, there's a reproducibility committee that has some ability to tie tenure and other stuff to this, which who knows if it's going to work, but maybe it will. And we got to make it easy to access compute and cultural change, which I was talking about. So here's a curriculum. It's a lot of little stuff. Just take a photo of the QR code, look at it later. There's no point trying to go through it here. But basically, these are the things we talk about. And in industry, strangely, a lot of people reach out to me being like, oh, we got a lot of people in my company, and I need to learn this stuff because our scientists are delayed, so fine, I can do a workshop on this. But it's actually interesting how much people come back to me later and say, I didn't believe in this, but it is not as hard as it looks, and it's really changed my outlook. So, if the best thing we can do is make everyone 20% more productive, this is like the most high leverage thing I could probably do in the world. And don't forget, the NIH cares a little bit, sort of, in the NIH-y way. There are these new rules on data management that are active, I think, now, and you gotta have a plan for sharing your data and your code. And I think starting now, you have to do it to get your grants. And so really, you have to think about it one way or the other. You might as well think about it and do it kind of properly. Journals, the better journals, are indeed requiring sharing. I mean, have you tried to run your code assuming you didn't know what you were doing? Like, assuming you started from tabula rasa, could you actually get your own code to work? And I wouldn't actually submit to journals until I felt confident that was possible. People don't test usability as much as they need to, and if you really want science to work, you gotta test it. One company, I mean, there's tons of people doing this. One company, CodeOcean, I invest in these guys, so that's my disclosure, I guess. But these guys are integrated with some journal, and they have, a way that you can upload like a container or whatever, so anyone can run it. Don't necessarily need to use this company. There are tons of people tackling it. Okay, what software best practices can we go to? Again, I'm going to repeat this. Use source control for every line of code that you ever write. It sounds annoying, but just do it. I promise you it will save you time. Even if it's just yourself that you're not collaborating with anyone, going back to be able to see what you did 2 weeks ago is just worth every cent. You have to use dependency management. You can use venv or conda or whatever, just do it. Document your code, write a design. Write basic tests. You don't need to test every line of code you've done, but the core things that, the mapping arm stuff, right? If you're doing something that if this goes wrong, your entire research is broken, test that stuff. And it doesn't need to be automated. It can be manual, right? Back in the day at Google when we were doing mobile stuff, before Android and iOS, we wanted to make sure that all the different, feature phones could access google.com. And there was no way to do automated testing. We just bought 500 phones, hired a bunch of people, and every time we had a new version, we're like, here is a process, you guys or people, just go and take all these phones, test everything out, and tell us if it works or not. And believe it or not, this cuts so many bugs. It doesn't need to be fancy, it just needs to be done, that's all. Use functions, version everything, and I think find an easy way to run your code. Hopefully I've shown you all this stuff. If not, please come harass me later. I'm always excited to talk about this stuff. I feel like it's a huge leverage point that we have to make the world better and to get more leverage and resources for scientists and to let you target bigger problems. You guys are much smarter than me, and I just want to be able to make sure you guys can do it faster. And if you want to teach this at your institution, just shoot me an email. I'm happy to help you guys out in whatever way I can. All right, thanks guys, and I'm happy everyone is awake.